I'm going to briefly demonstrate how to use interactive simulation that models the mixing of two ideal gases. These have to be different gases. We're doing this isothermally. We have two ways of doing it, either keeping the total volume constant. So if I look at this simulation below, we essentially have a barrier between two gases, and we remove this barrier, break this barrier. The gases mix, the total volume doesn't change. The other option, this compressed to the right, means we push this gas on the left side onto the right side, and whatever the volume is, in this case, the smaller volume. And in each case, we determine what the entropy change is. The simulation is on the LearnChemE site. Here's a link to the simulation. And so the entropy change, since it's constant temperature, only depends on pressure. If the partial pressure goes down, the entropy increases for a given gas. So let's look at this interactive simulation. Let's look at a case where the volumes are the same and the pressures are the same on each side. So the volume ratio is 1, pressure 0.5 for each. And if I click mix gases, then we can watch as they mix. Purple represents the combined color of the two gases. Final partial pressures are the same, half of those starting pressures, and the entropy change is the same for each of these gases. Well, let's look at a different case. Let's reset, and let's make the pressure of A significantly higher than the pressure of B. Let's also change the relative volumes. Now, if I mix the gases, so initial pressure B was 0.5, now it's 0.19 because it was a smaller volume, therefore fewer moles. Initial pressure of A, 0.87, now it's 0.54 because it was the larger volume. Entropy change is larger because we have more moles here. So that's one way of looking at the entropy change. Here's the total entropy change. Other is to look at if we compress to the right. So let's change this and now again start the same pressure, same volumes, and mix the gases. And what's going to happen, there's no entropy change. And that's because the final pressure of B is the same as the starting pressure. Final pressure of A is the same as the starting pressure. Well, that wouldn't be the same if we change the volume ratio. We started the same pressure, but now we mix the gases. And notice the partial pressure B hasn't changed, so the entropy did not change. But the partial pressure of A, which was originally 0.5, is now 0.9. Pressure increased, the entropy decreased for molecule A. Remember, these are ideal gases, but the same concepts would apply if they're real gases. The actual numbers would certainly differ.